We are Group 1, and this is our Beast project, the Scream Mask using a Type K thermocouple. So what is a thermocouple? A thermocouple is a sensor made of two dissimilar metals that generates voltage relative to the temperature difference between these two metals. It is widely used in industries for precise temperature measurement. A Type K thermocouple works due to the thermoelectric effect. This is the junction of the two metals, chromel and alumel, producing a voltage that correlates with the temperature difference between them. A Type K thermocouple can measure temperatures between minus 200 degrees Celsius and 1250 degrees Celsius. It is known for its durability and heat resistance. The temperature can be calculated from voltage by using a ninth order polynomial formula. Different thermocouple types have different coefficients, so as part of our research, we found those pertaining to type K. Our main goal for this project was to use the thermocouple wire to measure and visualize the temperature of simulated blood flowing through a Halloween-themed scream mask. We found a scream mask that came with a blood pump which allowed prop blood to flow through the mask. Measuring changes in temperature of the blood over time would accomplish our measurement goal while fitting the theme of the project. For the design of our measurement system, we needed to take a couple items into consideration. The first was deciding how to protect the thermocouple wire from the surrounding liquid. What we did was wrap the probe end in copper tape, which is highly conductive and had no significant impact on the sensibility. Doing this would allow the thermocouple to get accurate temperature readings without coming in direct contact with the liquid. We also needed a way to integrate the sensor into the mask and pump system. What we did for this was puncture a hole through the bottom of the mask above where the blood re-enters the tubing, which allowed the entire blood flow to pass around the thermocouple wire. The final materials for our build were the scream mask, the tubing, the heart pump, the simulated blood, which was made of corn syrup and red dye and included inside of the pump, as well as our Type K thermocouple, the copper wire, and the NIDAC in the lab. To get data from our thermocouple, we needed to create a VI file in NI LabVIEW. Initially, we added the DAC assistant to make sure our thermocouple was connected properly and collecting data. Once this was done, we took and modified analog data programming from recitation assignments to get both numerical and waveform outputs for the thermocouple. This included an analog DBL 1 channel 1 sample for numerical output, and analog waveform 1 channel 1 sample for waveform output. LabVIEW let us specify that our analog input was a Type K thermocouple, so the equation we found was already built into the program. We added inputs to our control panel for the sample rate and number of samples to allow for easy adjustment while testing. We also added a subtraction function to the waveform x-axis to show elapsed time instead of absolute time. This is the final block diagram and control panel for our VI. It includes the inputs for the sample rate and number of samples and allows the user to select the physical channel from the DAC. For the waveform, the x-axis is time starting at 0 and it auto-scales to show all of the data recorded through the current time. The y-axis is temperature, which also auto-scales. There is a numerical output for the current temperature in the bottom right. To calibrate our thermocouple, we tested it by comparing numerical output to known temperatures. These were found by using a thermometer to verify the temperature of the room as well as other objects warmer or cooler than the room temperature. This included items such as a laptop charger and a computer, which were both much warmer than the room, as well as a water bottle, which was cooler. Once we determined these to be accurate, we covered the probe with copper tape to see if there was a difference. Since there was no noticeable differences, no adjustments to the function were necessary. It was now time to build the rest of our physical system. We first wrapped the rest of the probe end of the thermocouple in the copper casing. We then punctured a hole in the bottom of the mask with enough room to insert the thermocouple into the blood flow. We then sealed off the bottom of the mask with layers of tape to prevent leakage. After that, we attached the heart pump to the tubing, which flows around and into the mask. The pump, which was pre-filled with the simulated blood, was kept at a cold temperature through the start of testing. This allowed us to see the decrease in temperature of the blood as we recorded data for the first time. After this, we inserted the pump into a thermos of hot water and ran the test again to show the increase in temperature. We will now show you the results of these tests. In conclusion, we accomplished our goal of creating a functional measurement system. Another success was educational value. We learned a lot about how thermocouples work, and we also gained a lot of experience using LabVIEW. One particular challenge we faced was the amount of time that we could all meet in the lab to work on the project, which was limited. However, we still were able to accomplish our goal in a timely manner. We also experienced shipping delays for the mask and pump, but thankfully that didn't slow us down as we could focus on other parts of the project while we waited for that. Some potential improvements we made note of as we were working included sealing the hole with glue instead of tape. There was more dripping than we expected, which didn't affect the results of our testing, but it would have made cleanup a lot easier if there was less dripping. We also believe we could have enhanced teamwork in the lab and worked more efficiently. This project will make it easier to explore additional applications for thermocouple systems in more complex environments now that we understand them better. Overall, all members of the team were willing to communicate in any possible way, especially since Ian and Sungyeon are deaf students. While it was challenging, we found a way to make it work and had success. The schedule wasn't an issue as we found the time to meet, to discuss, and help each other out to get better ideas.